Okay, so let's resume. So here I introduce one property of proton. Well, proton is a big business in the development of physics as well, as you will see later in an extension. So it is a fermion spin half, and therefore it's natural to associate with it a magnetic dipole moment. And because its charge is plus E, we don't have the minus sign as in the electron in the relationship here. The current loop is positive, give us, the motion is the same as the current loop, and then we have this magnetic dipole moment. And that can be measured, and the value is known. We just talk about how tiny the effect would be for nuclear spin splitting, because the nuclear magneton is 3 orders of magnitude smaller than the Bohr magneton of an electron. Now, what we are going to discuss for the mechanism behind the hyperfine structure is the interaction between the electron spin magnetic dipole moment, or the electron spin in short, with the proton spin or proton magnetic dipole moment. They are both spin half. When the two things interact, it is natural that the interaction term will come out to be related to the spin of proton dot into the spin of the electron. A classical way, but not quite right, to think about it is that in electromagnetism, you know, when two magnetic dipole moments are close to each other, there is an interaction energy that is related to the relative angle, the alignment, how they align between them. Okay, so look at Griffin's, you will find an expression which is the dipole. This is magnetic dipole moment. So dipole interaction term. Now, that is a way that you can immediately get at the dot product form. So all I want to take from more detailed discussion of the interaction between these two magnetic dipole moments is the form that goes like spin of proton dot into the spin of the electron. Now, each of this is a spin angular momentum, thereby there is a h bar in here, h bar in here in units. To make this thing don't carry any unit, we can divide by h bar, okay? And in this form, there's no unit here, just a number, that's just a number, and then this must be an energy. So I will be using this as our discussion, as the basis of our discussion. So A will set the energy scale. We expect that to be tiny because that will involve the nuclear magneton here. Then there will be no new physics because it is a spin half dot into a spin half belonging to two different objects. When we see this, we can use the total angular momentum due to the two spin halves. But we know how to add spin half to spin half. We discussed that. There will be a S equals 1, we call triplet. There will be a S equals 0, we call singlet. So the situation is the same as before. This is nucleus, it could be up, down. This is electron, it could be up, down. We have 4 states, up, 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 down, down, up, down, down. Okay? This 4 combination can be described using the total S, and then 3 of them belongs to 1, the triplet state, 1 belongs to the singlet state. So no new physics after we take this form into consideration. Okay, so thereby we can at least write down something for the splitting due to the total angular momentum quantum number. So we have this form, we play with that. But we know how to do that. We define the total, thereby the dot product will be described by something like that. It's just like our L square minus J square minus S square minus S square before. But now we don't have the orbital in our sum, but the origin has to do with two spin half. One belongs to the electron, one belongs to the proton. That's it. So with this description, we use the total as the description. Then we know this is half due to proton, always half. This is always half. It is the expression like this. Then we know the triplet one will have a different energy than the singlet one, right? So without the hyperfine splitting, we can use the description of not adding them up, okay? So electron is half, proton is half, and we have this being plus minus half, this being plus minus half. These are the four states I referred to. That is the description when the two things don't couple. But when the two spin couples, it is better to change basis or change to the total angular momentum description. Therefore, we will have S, MS, with S taking on 1, triplet, 0, singlet. All right, 4 stays here and 4 stays here with this thing. Okay, no more, no less. But when you have this hyperfine splitting, this description should be used because that will immediately give us the splitting in energy according to the total angular momentum that I use a capital S here because the origin are both spins. So according to S equals 0 or S equals 1, that will take on 2 numbers. All right, the A is an energy in the interaction term. We don't work out this in detail, but I will show you the expression in a while. Okay, so let me extract the result out. We have this very last expression when we have the two spins, something like that, or like that, and another combination is this plus that, this plus that, S equals 1. This combination will take on plus 1/4. Okay, and for the singlet, this is 0. This will take on minus 3/4. Meaning, depending on singlet or triplet, the energy will be A over 4 or minus 3A over 4. So the hyperfine term, hyperfine interaction term, will split the hydrogen ground state into 2 closely spaced, that we expect that to be 10 to the minus 7 to 10 to the minus 8 eV. Okay? Into 2 very closely spaced levels. So here is the picture. 1s ground state of hydrogen, but when we include the nuclear spin effect, that will split into slightly higher A over 4, slightly lower minus 3A over 4. Notice that this is not equal to that, right? Because one is plus A over 4, one is minus 3A over 4. Now, for those who know a little bit of statistical physics, because once someone told me that you know Ising model, Okay, now this is also related to that. You have alignment or anti-alignment taking on two different energies. In statistical physics, many of you are taking one course by Professor Go now, I think. You play with temperature. You have temperature KT. So you have the competition of two energy scales. One is this difference, A. Another one is KT. Depending on whether that thermal energy KT is bigger or smaller than these two levels, the behavior of the system will be different. High temperature, these two states will be equally populated, and then you don't have a net spin alignment. Low temperature, this one will be aligned more, will be occupied more, therefore the singlet state will be preferred more than the triplet state. Okay, now that much for statistical physics. Let's go back to quantum for the moment. So here you see what is called the hyperfine splitting in hydrogen atom. It is referring to this particular splitting into two levels of the ground state 1s. Of course, we can carry out the discussion for the higher state, okay? But most relevant to frontier research is this ground state 1s splitting. Next question, how big is this? Well, you know the name, hyperfine, that means not big, but how small? Now that is related to what is the prefactor A. The splitting is A, right? I claim an expression, but I don't derive it for you. But you can look it up for the magnetic dipole moment, the magnetic dipole moment, then you multiply them together. It's basically will give you this prefactor. So it is this whole chunk of constants. Mass of proton, mass of electron, okay? And then the Bohr radius for power, the proton G factor, because that is related to the proton spin, okay? It is also related to the electron spin. So basically it's a G factor. There's a G factor of spin here, 2 here, there's a factor of 2. And then there's one factor of mass of proton because of the magneton of proton. There is one factor here of electron because it's the Bohr magneton. Then you see a MEC square, a rest mass of electron, then you have the Bohr magneton, okay? Quite natural combination of constants. But I claim this in order to give you a number. You plug in all the things, that happens to be 10 to the minus 6 eV. Okay, pretty close to our expectation. Now, this was first measured in experiments on hydrogen by this group of physicists. Among them, Ramsey from Harvard got the Nobel Prize in 1989, partly for this work. And Kepler is someone that you know. If you learn lower level year 2 mechanics, he wrote a very good textbook. And if you work on atomic physics, in recent years in co-atom business, he's also a major character. So now go back to the number. So it is this splitting here with this energy. What does it mean in experimental numbers? The frequency for this transition is 1,420 megahertz, or in very accurate measurement is this number. Okay, and this number as I told you, was first measured very accurate by this group, and then there's the Nobel Prize awarded. Now, it is an important number to remember, actually, because when you turn it into a wavelength, this transition, the EM wave come out, it has wavelength of 21 centimeter. So for those who like astronomy, when you read things, you encounter something called the 21 centimeter line of hydrogen. It is referring to this hyperfine splitting transition. Okay, now this line happened to be, it can travel through atmosphere, it can arrive on Earth, so that you can look at it by big radio telescopes. So let me summarize the picture one more time. At the beginning of the discussion, we were here, okay? Hyperfine splitting here, relativistic effect, but vacuum effect here, all right? But when we take into account of the nuclear effect, nuclear spin effect, we have the hyperfine level. I have been using S as the label just not to introduce any fancy symbol, just focus on the physics and emphasize that there's no new physics, adding to spin half. But in the literature, usually the total, I mean the electron and spin total, angular momentum carry the symbol F. So here, F is 0 means our S is 0, okay? I don't want to introduce too many new symbols to confuse you about the physics. No new physics, adding angular momentum, that's it, okay? And this particular ground state splitting is the 21 centimeter line. So this assigned, I will not go through it, is just to get you back into the standard notation in astronomy book or in nuclear physics books. Is being used, the F symbol is being used, but the physics is the same. Why we are discussing here so tiny an effect? For several reasons. Reason number one, I encourage you to look at the definitions of SI units of different things. For example, the SI unit of time. You look it up from the, there's an official site, IUPAP. They meet every 3 years to see whether we need new definitions for the basic units. So the current definition of 1 second is as follows. Take a cesium atom. Look for its hyperfine transition, the hyperfine splitting, the difference in energy, okay? And that will give you a frequency, just like our 1420 megahertz. For the cesium, it was measured to high accuracy. That frequency is taken to be exactly, there's no plus minus, no error in the definition, okay? It is taken exactly to be this time per second, that's hertz, right? You flip it, that will give you the definition of what 1 second is. That is the current definition of 1 second. You see, in order to understand scientifically what is the definition of 1 second, you need to go through quantum mechanics, perturbation, a lot of effect about angular momentum to the end. Cesium atom. Now, you don't understand cesium atom yet, right? Many electron atoms. But it is 6s1. So it's more or less like the hydrogen. You could expect that 6s state will have a splitting. You look for this particular transition, that is exactly that hertz. Flip the number, it becomes the definition of 1 second. You see? Okay, that is how science goes. I don't know, 20 years later, maybe there's another new definition, because some other experiments will become more accurate than this. Usually, the most accurate, experimentally accessible quantity will be used as the definition. As a remark, 2 years ago, on this day, the kilogram was redefined. Again, very quantum stuff, by the most accurate determination of the Planck constant. The definition has to do with taking the Planck constant as an exact value, highlighted here. No more plus minus thing. Take this as the exact number, then what 1 kilogram can follow. Okay, now very strange thing. Even a kilogram, you buy something from the supermarket, has a quantum basis now. So congratulations, you're a physics student, you know more quantum mechanics than I think everybody on campus, okay? And you need it for living, well, ordinary life. Okay, another reason is that it is the basis of radio astronomy. Because of this line, is so low in energy. This megahertz, 71 centimeter, or in EV is something like that. Okay, now many of you are learning thermophysics. Turn it into a temperature, it is 0.07 Kelvin. And you know, from Big Bang, as the universe expands out there, there's a 2.7 K background. So in this heat bath, and hydrogen, if there are any matter out there, hydrogen is the most abundant. You know, you start from some energy only, and then quark gluon plasma forming proton, and then you have electrons, and then you cool down, you start forming neutral hydrogen. If there is something out there, hydrogen is the most abundant. Also, the density out there of hydrogen is so low that only very occasionally 2 hydrogen can come together and negotiate to form a lower energy bound state H2 molecule. There are some out there, but hydrogen atom is still the more abundant one. Okay, so that is the source of why we can detect this particular line by telescope on Earth. And when you see such beautiful pictures of galaxies, actually they are taken from the Doppler shift of this 21 centimeter hydrogen line. Of course, what you measure is not always 21 centimeter. Some part is moving away from us, some part is coming towards us. Thereby, you can map out this spiral, beautiful picture in force color. Okay? And some of you might have attended a curriculum 10 days ago, no, last week, I think, by the chief scientist of this instrument in Guizhou. It's called FAST. It is at this point the most powerful radio telescope on Earth. So it's 500-meter aperture radio telescope. I encourage you to look into their website, because every big project has to justify its building and existence, because a lot of money has been invested. And you will see the first scientific goal of this big setup is to do something called the H1 line survey. When you see in astronomy, H, this is a Roman letter 1, okay? This is H1 line. It means what we discussed, 21 centimeter line, okay? So it aimed at doing a wider angles full sky survey, so-called, of this 21 centimeter line, so as to look for a lot of things. I think they have achieved looking for many binaries in about 15 months than anything before. So the very last remark about this part of hydrogen plus something. There are things that I have not discussed along this line. For example, finite mass of the nucleus, because you have done that in the last term. You know, we better use the reduced mass. That's okay. And then how about isotope effect? How will it change the hydrogen spectral lines if we have a neutron in the nucleus? Okay, so it is a this is a deuteron, right? So in the nucleus, you have one proton, one neutron. How will it change the physics of a simple hydrogen atom? A very interesting exercise will be, proton is believed not to be a fundamental particle, because in standard model, in particle physics, we know that quarks are the fundamental particles, but not proton. Inside the proton, there are quarks, there's something inside, and interacting through exchange of gluons. Therefore, proton is not a point particle. It has a finite size. A big problem actually is, what is the proton size? Believe it or not, even up to now, many groups are still arguing about what is the size of a proton. Now, an interesting exercise will be to assume the proton to have a finite radius, finite size, and then you look at Griffiths. A uniformly charged sphere will have potential energy like this. Okay? Well, it's still central force, it's still spherically symmetrical, but instead of a point at 0, 0, 0, you assume this and then see how it will change the energy levels of this new hydrogen atom. In particular, how will it change the 2p to 1s transition energy as a function of the radius? Okay, now let me tell you, this is exactly the idea behind using the transition line to determine what is the radius of the proton. That is to say, how big is the proton. Okay, now you can look into the papers or literature, and you will find very high precision spectroscopy on hydrogen atom aiming at determining this radius. And let me tell you, this problem can be done using perturbation theory. Then some final remarks. And then how about antimatter, anti-hydrogen? And then let me tell you, anti-hydrogen is the only neutral antimatter that has been fabricated on Earth. Using an anti-proton, well, you have many of that in CERN because it is a PP bar collision experiment at CERN for the Higgs discovery. So anti-proton they have. And then positron, there are many. You know, positron is now being used in the hospital. PET scan. So you have that, you can generate anti-electron, positron. So positron trapped by an anti-proton, that will be an anti-hydrogen. It's a very difficult thing to do. Those are energetic. You have to slow it down, but how to slow it down? You use matter to slow them down, annihilation. Matter, antimatter, annihilation. So they will destroy each other. So very difficult thing. Nonetheless, CERN, there's a CERN team produced the anti-hydrogen, and they measure 2p1s transitions to high accuracy. Okay, they even measure the lamp shifts, so you can appreciate, you know, the knowledge of hydrogen atom actually is playing some role in the frontiers of physics. Okay, so this ends the part of hydrogen atom plus something. And for those of you who want to read more, or you want to know where you are in terms of a few standard textbooks, I list a few here, okay? And then technique-wise, we cover a little bit more than reference. For atomic physics, this is a standard undergrad textbook where we have covered a few chapters. The remaining ones we will do a little bit later. And then very serious quantum mechanics and atomic and molecular physics can be found in these two books by the same two authors. These are two separate books, okay? But they will take you slightly beyond undergraduate level. This is a book that we use in a postgraduate course on atomic physics by Professor Wang Dajun. I think we have covered the first 6 chapters. And then for the chemistry version of this discussion, we have covered quantum chemistry, a classic book, and then we have done these 2 chapters. Okay, so let me mix an optional discussion. You can find a separate document that I post into Blackboard. A few frontier topics related to what we discussed in our course as the background knowledge. So what I want to do is that just to convince you that at this point, you can understand some frontier research by yourself. The first thing is something that I already mentioned, antimatter and matter. Do they behave the same way? Now that is what we believe in. But for physics, we better do experiments to check that, okay? Now, the only thing one can do so far is anti-hydrogen, neutral. But in CERN, they achieve over about 5 years or so, they can form this, and then they can keep it long enough in time to do spectroscopy, to do spectrum, to get spectral lines out of it, okay? So here are 3 kind of classic papers, all in Nature, the top journal. So 4 years ago, they look at 1s2p Lyman line transition. So they, at that point, they can only observe it, well, with some accuracy. But then 2020, they can do the fine structure. That's really good. Spin orbit interaction, they already see that, okay? But a few months ago, they play something even fancier. Now, in the lab of Professor Wang Dajun, he used laser cooling. So use 6 laser beams to trap some atoms there, so-called cool down them to something like 10 to the -7 Kelvin, 0.0000001 Kelvin. So that is called ultra cold atom, ultra cold molecules. So A few months ago, some members of this CERN group did something similar, but they used laser to trap anti-hydrogen. So this is a very not famous, a very well-known paper in 2021. I give you the link. You can click on them if you start with CHK site, because we have paid for the subscription fee for the journals. Another problem I already mentioned about is how big is a proton? Well, that is a long story, but basically what I would like to point you at is that for many years, there are different groups using two kinds of techniques. One has to do with scattering of electron out of proton. So you fly some electron in and then see the angle of scattering. You see how strong this potential field is, so that you infer how big is the proton. Another one is to use spectroscopy of muon hydrogen. What does it mean? Instead of the electron, I replace it by electron's cousin, muon. So I have a proton trapped in a muon. Muon has minus E charge. Okay, and then do transition. Look at the spectral line and try to see how big is the proton. It so happens these two parties, there are several groups, is giving a number that is slightly different. Okay, one group says is 0.87 Fermi or femtometer. Another party said it is something like that. Okay, well, not off by much, but all the error bars included, they don't overlap. Okay, so that is an interesting problem. So for those who are interested, you can read some introductory journal magazine article introducing the background. And then now, 2 years ago, three years ago, there are new experiments coming in, scattering experiment reporting new results. And then even most recently, a few months ago, this problem was revisited and summarizing what happened in recent years about these two different techniques in probing the same thing, yet the results are not coming together, okay? But the latest thing seems to be the two kinds of results are converging at the end, all right? So 2 years ago, there's some very high frequency, highly accurate spectroscopy done in muonic hydrogen. Again, it is not quite the same as scattering experiment. So early on, I mentioned this latest development is called the muon G-2 experiment measuring the G factor of muons. So for those who are interested, go to the Fermilab site. They have a website for this particular experimental collaboration. Basically, the situation is that theory, using all the forces, all the particles we know in the standard model, this is the best value. And then using all the experimental data from different groups, including the Fermilab latest experiments, it is this number. Well, not too bad, starting to be off in the last 4 digits, okay? But the difference is significant enough to hint at there may be some new physics beyond the standard model. So for those who want to read the very first experimental data published, this is the paper to look at. Another problem, I don't know much about it, is how proton get its spin. Where does its spin come from? Now, of course, we know there are at least 3 quarks and some gluons in it. And quarks also carry spin, right? So how can this sum up the quark's spin, sum at the end, give rise to proton being spin half? Well, it turns out to be a long-standing problem in particle physics. Okay, so for those who are interested, I also give you some references. All right, so that will take you to some interesting topic beyond our course. So for the interest of time, I would like to start the next part just to set the stage for next week's discussion. So far, if we look at the whole periodic table, we have understood quite a bit of thing about the first element, hydrogen. Good reasons for that, because for hydrogen, the bare part, we know the exact solutions so that we can use our tools to handle hydrogen plus a little bit of effects. Perturbation will be very effective. However, there are 90-something atoms beyond hydrogen in the periodic table. Helium, lithium, beryllium onwards, right? So is it possible to do some quantum mechanics on these multi-electron atoms? So that is the topic of the second part of our module on the physics of atoms. So for this very first section of the discussion, I would like to convey one simple message. We know the quantum mechanics equation. We know what is the problem. However, the quantum mechanical problem of solving any multi-electron atoms is a very difficult problem. No one can solve any multi-electron atom exactly. No analytic results. Okay? We should be happy about it. That is to say, we are not, in any way inferior to anyone. No one can do it, no matter how strong you are mathematically. But we will not give up. We want to understand the physics of these atoms. How can we do it? Approximation. We want to keep the beauty of the description of the hydrogen, 1s, 2s, 2p. So in this first part, I would like to convince you, when we describe multi-electron in this language of something like a hydrogen atom, this is an approximation. Okay, so I would like to do this simple point first. Then we will go on to develop how we can make this approximation and how good is this approximation. What is the approximation behind this description? Okay, let me tell you at the end, this description has been very successful. Otherwise, there will be no chemistry work. All the chemists think along this line, and they have been very successful. They can make good medicine for us, right? Okay, so how can we possibly treat a problem that cannot be solved in terms of such a useful description? Okay, it is an art and a science. So let's start. First point, quantum mechanics works for hydrogen and for many electron problems, generally called many particle problems. We know how to write down the Schrödinger equation, only it is very difficult to solve. sometimes no one can do it. Okay, therefore we knew some new ideas and approximations in this part of the course. We want to reduce the helium problem or lithium problem or the uranium problem, element number 92, to some single electron Schrödinger equation. So that can only be an approximation. How can we do that? Okay. Then a second related question is, let's say we can do it. So we have this 1s, 2s, 2p states. How can we fill the electrons in? Uranium, we have 92 electrons. What is the rule? You know the answer, Pauli exclusion principle. But we want to know a little bit more. What is the quantum mechanical statement about the Pauli exclusion principle? It turns out the statement has to do with some symmetry requirement of the wave function in describing 92 electrons or 2 electrons in a helium atom. So the first thing is to convince you that we know the equation, we can't solve the equation. Okay, so very humble task. It's hard to solve. Let's think about an atom, the Z atom. So charge plus ZE in the nucleus, and then we have Z electrons. That is the Z element, right? Z is the standard symbol for atomic number that label which element in the periodic table. All right. So in hydrogen, what we have done is that you did this last term, I did that this term, right? Okay. So, but the reason why you did this last term is this Coulomb term is the most important. So here, for other atoms, again, we will focus on the most important one. That is to say, the Coulomb term due to the nucleus. We will focus simply on this term. For the discussion in our course, we will ignore all these smaller effects for the bigger atoms. All right? Now, let's write down the Hamiltonian for this general atom. We assume the nucleus to be fixed as 0, 0, 0. If you are not happy, take it as Z plus 1. Particle system, you do classical mechanics, center of mass, etc. This is your business. But for me, I'm happy with putting the nucleus at the origin 0, 0, 0 and only look at the physics of the Z electrons. So we have kinetic energy for the first electron, second electron, and the Z electron. So these are the kinetic energy terms, simple, okay. And then each electron will see the nucleus. So there will be a Coulomb attraction, right? So minus ZE times E, so minus ZE squared divided by the separation from the origin of electron number 1, number 2, number Z. So these are the electrons seeing the nucleus attractive Coulomb potential energy. All right, simple, still simple. And electron will interact through the Coulomb interaction. They are of the same charge, thereby there will be a positive potential energy due to Coulomb interaction. So it will give rise to E squared plus this constants, and then 1 over the separation between 2 electrons. And then there are pairs, right? Ez times Ez minus 1/2 pairs of electrons. They interact in pairwise, right? So this sum means sum over these pairs, okay? So now we have the Hamiltonian. So do you understand what this Hamiltonian is? Right? Therefore, let me show you the Schrödinger equation and then I will stop. So the Schrödinger equation will be the Hamiltonian times psi into each term equal the allowed energy for the atom times the wave function. So equation 2 will be the governing quantum mechanical equation for any atom from hydrogen down to element, I don't know now, maybe 119 in the periodic table. Okay, so point number 1, we know how to write down the quantum mechanical equation governing any atom. Second point, we cannot solve this exactly. Okay, it is difficult to do it and nobody can do it. However, still, we can do it very accurately, but approximately. The chemist can buy a package and calculate the energy levels of any atoms in, I think, a few minutes at most. Okay, but what is behind those numerical package? What are the physical thinking go into approximating this problem is the focus of our discussion. Okay, so next time I will continue the discussion on bringing out the difficulty of this particular equation and then how we can try to bypass the difficulty and move on to get a good understanding of the atoms. Okay, so I will stop here today. I will stay around. If you have questions, you're welcome to ask.